All right, finishing up this section. Next on the menu is the Graham-Schmidt process, which you should be familiar with from sophomore linear algebra. We give a technique to take any basis for vector space and transform it into an orthonormal basis. The technique is involving projections, that's why it's in this section, to take x1 through x sub m, a set of linearly independent vectors from Rn. So they are a basis for their span. They're linearly independent and they span what they span. So they're a spanning set for their span. So they are a basis for something. They're not a basis necessarily for Rn, but a basis for something. So we are indeed turning a basis into an orthonormal basis. So we start the process by defining x1 tilde, make it a little bit bigger. x1 tilde equals x1 normalized. Okay, these are basis vectors. None of them could be the zero vector. We're okay with normalization. And then recursively define for k equals 2 through m, define x sub k tilde, the kind of transformed version of x sub k. Define it to be x sub k minus the sum from 1 to k minus 1 of x sub I tilde, inner product with x sub k, times x sub I tilde. Now what you got here, trust me in the short term, what you've got here is a projection of x sub k onto x sub I. So we're subtracting off all of those projections. Does it look like a projection? It does if we're dealing with a bunch of orthonormal vectors, if these x sub I tildes are orthonormal. So that's part of the story to be told. They're certainly normal because here we're defining x sub k tilde. Whatever we've got here, we've divided by the norm of that vector. So indeed, we're looking at unit vectors. And we'll put some geometry on this and draw pictures as best we can to inspire that this in fact does transform the set x1 through x sub m into a new set x1 tilde through x sub m tilde, and this new set's an orthonormal basis for the span of the old set. So we've changed any old basis into an orthonormal basis. Graham-Schmidt process. Okay, let's actually shrink it down a little bit now. Let's try to get the computation in front of us at the same time as we have this little conversation. All right, for 1 to m, we have that x sub k tilde is a linear combination of x1 through x sub k. All right. If I look at x sub k, indeed it's a linear combination of x1 through x sub k. X sub k involves, x sub k tilde involves x sub k. X sub 1 tilde involves x sub 1. It's up here. X sub 2 tilde involves x sub 2 and x sub 1. X sub 3 tilde involves x sub 1 tilde, x sub 2 tilde. So we do get the dependence of x sub k tilde in terms of these x1s through x sub k's. It's a little hidden. I explicitly see the x sub k and the x sub 1 through the x sub k minus 1. They're contained in these x sub I tildes. So we do get this kind of relationship. It's a little hard to see because it's the fact that we've defined these things recursively. In order to compute x sub 3 tilde, I need x sub 3, not a problem, and I need x sub 1 tilde and x sub 2 tilde. To define x sub 4 tilde, I need x sub 4, not a problem, and I need x1, x2, and x3 tildes. So recursive definition does give us that kind of dependence. X sub k, not x sub k tilde, but x sub k is a linear combination of x1 tilde through x sub k tilde. Now that I can explicitly see. Here's x sub k, and it's in terms of x sub k tilde and x1 tilde through x sub k minus 1 tilde. So I'll do some multiplying around, and I can actually write x sub k explicitly as a linear combination of x1 tilde through x sub k tilde. And this is holding for all appropriate k. So we get x sub k, a linear combination of these associated transformed vectors. So the span of x1 through x sub k equals the span of x sub 1 tilde through x sub k tilde, because of these two observations here. In addition, we noted above that the projection of y onto x subtracted from y is perpendicular to x. This is where we had the right triangle upstairs. So we get the orthogonality when we have this type of thing, and that's exactly what we're looking at back up here. We've got x sub k, and from it we're subtracting projections. Those projections will be orthogonal to what we're projecting onto. We're projecting onto, let's see, the vector x. It's the vector that appears in the inner product. We're projecting onto x sub 1 tilde. Then we're projecting onto x sub 2 tilde. It's also the vector we get over here when doing projections. In general, projections, we had to divide by some norms, but we're dealing with unit vectors here, and that's not necessary, as we've normalized them as we've gone. All right, so that means we're getting x sub 2 perpendicular to x sub 1. We're getting x sub 3 perpendicular to x sub 1 tilde and x sub 2 tilde. Should be reading these as tildes. We're getting x sub 4 perpendicular to x1 tilde, x2 tilde, and x3 tilde, because of the way we've defined these things in terms of projections involving the x sub I tildes. Of course, these things are normalized. That was easy to see. This orthogonality stuff's a touch more subtle. So what we've done is created an orthonormal set, or an orthonormal basis, for the span of those m vectors. Now, this is not a complicated computation. I mean, it's potentially tedious, but it's not a complicated computation. There's kind of an algebraic argument as to why it works. Let's illustrate it with pictures. So here comes some vectors in Rn, and here comes some stuff about standard position. So if you think in terms of projections and shadows, the Gram-Schmidt process should make perfect geometric sense. All right, so here's a little picture. Suppose we've already found x1 tilde, and we found it to be the first standard basis vector. We found x2 tilde to be the second standard basis vector to make my pictures a little more manageable. And suppose x3 is given as this vector here. All right, so what we've got is we've gone through the process of taking this vector x3. We've projected it onto x sub 1. Is what we would have done in the normalized. So x sub 1 must have been a vector along the x-axis. X sub 2 must have been a vector along the y-axis. And we've projected and normalized. So anyhow, what comes next is the following. All right, so the way we're going to create this is, I think I misread that, x sub 2 had to be a vector with a component in the y direction. You know, it could have possibly had a component in the x direction as well, in the E1 direction. So what we're going to do is we'll illustrate over here is subtract away the earlier pieces. So x sub 3 is made out of a component that points along the x-axis, this component that would be given, indicated by the box, a component that points along the y-axis, and a component that points upward. Okay, so the way we're going to find x sub 3 is to take, or x sub 3 tilde, is to take x sub 3, project it along x sub 1 tilde, projected onto the tildes. We project along this direction, and that'll actually produce that vector that lies along the x-axis. We'll project along x sub 2 tilde, vector that points along the x-axis. That'll produce this blue vector here. And what's missing is an orange vertical vector. Now, if I'll take the green vector and the blue vector and the orange vector, mutually perpendicular, add them together, that'll give the x sub 3 vector. Parallelogram law of addition with 3 vectors. I draw a box instead of a parallelogram maybe. Okay, so how is x sub 3 computed? Well, that's fairly easy if we can find the green vector and the blue vector. We'll know green vector plus blue vector plus unknown orange vector equals red vector. Solve for unknown orange vector. We'll find it by taking x sub 3 and subtracting off the green vector and the blue vector. So think of x sub 1 as contributing direction along the x-axis. X sub 2 contributes maybe some direction along the x-axis, but also some direction along the y-axis. Well, we subtract off the piece of x sub 2 that points along the x-axis. Subtract that off. That's what happens in the subtraction of the projections. And we just keep the new direction that's perpendicular to the old. We find x sub 3. The orange vector would be what we'd get by taking x sub 3 minus those 2 projections. I do still need to normalize it to get x sub 3 bar. So maybe we shrink it down until it's a unit vector. What we end up with is the first, second, and third basis vectors in this particular illustration. But whatever you do, those first 3 vectors you get, they're going to be mutually orthogonal, and they're going to be unit vectors. And that process will continue if we had more than 3 vectors. But think shadows as projections and think subtracting away directions. So this very much involves that informal idea of vectors having directions and almost gives us a tangible, almost gives us a rigorous idea of what a direction is. I'd say in 3 dimensions, there's 3 fundamental directions. I could choose a bunch of different possibilities for those 3 fundamental directions. The most obvious one is using the standard basis vectors. There's a direction along the x-axis, along the y-axis, and along the z-axis. But I could, rotate those things around and have 3 mutually orthogonal basis vectors that don't point along the x, the y, and the z-axis, but point some other oddball direction. So this is easier to visualize, and the reason I chose to make the first 2 x1 tilde, x2 tilde is the e sub 1 and e sub 2 is to make the picture easier for finding the x sub 3 tilde. All right, so think projections and directions, and you're good to go. That's why, geometrically, why the Graham-Schmidt process works the way it does to produce a nice basis from any given basis. Hey, why do you like orthonormal bases again? It's a piece of cake to write a vector, any vector, in a vector space in terms of an orthonormal basis. It was corollary 2.2.2, the Fourier expansion, they called it. All you got to do is take that vector and project it onto the first basis vector. If it's orthonormal, that projection is an easy computation. It's an inner product. That's the coefficient for the first basis vector. Project the given vector onto the second basis with an inner product, and so forth. And so the coefficients are easy to find when you have an orthonormal basis. That's why we want an orthonormal basis. How do you decide if you want nice IJKs pointing along the axes or something else? Well, that may depend on the bunch of vectors they gave you as a spanning set. Or you might be doing some physical problem where you've got some vectors that are special for some reason. So common applications of this stuff is differential equations, where you find a solution space for a system of linear differential equations with constant coefficients, say. Something you may have done in sophomore DEs, Probably not, because it requires linear algebra. If you had an undergraduate applied math class, you would have covered those kinds of ideas. But there's multiple settings in which you would want to apply this Gram-Schmidt process. We'll talk history here right now. And in fact, here's Jorgen Gram and Erhard Schmidt, for which this technique is named. And just a little history to give it some context. And funny thing, these guys weren't thinking vectors in Rn when they came up with this process. Jorgen Gram, Danish mathematician, worked for an insurance company, published papers in forestry, probability, and numerical methods. He publishes a paper on series determined by the methods of least squares in Journal for Mathematik. And this paper contained the process, the Gram-Schmidt process mentioned here. Whoops. Though Laplace and Cauchy had used the technique before, I mean, it's an obvious geometric approach. The name gets stuck. Gram-Schmidt process, as often in math history, they're not the first folks that come up with the idea necessarily. They're just the folks who maybe published it first, or names get attached to theorems, sometimes not for all the right reasons in terms of justifying who did the initial work. The thing here is Gram, he's looking at integral equations. Real quick comment. A differential equation is an equation with derivatives in it, and the unknown is a function. Integral equations are equations that's got integrals in them, and the unknown is an integrand, possibly, or piece of an integrand. So there's an area of math, in fact, called integral equations. But Gram is dealing with integral equations when he comes up with this idea. Gram, oddball story, he never taught math. We mentioned the other things that he did. Some real trivia here. He's hit by a bicycle and died at age 65. Schmidt, of Gram-Schmidt, was born in Estonia, did his doctoral work at the University of Göttingen under Hilbert's supervision, did most of his career work at the University of Berlin, also studied integral equations. So what these guys are doing when they're applying the Gram-Schmidt process, this orthonormalization process, they're not dealing with vectors in Rn, they're dealing with something else. They're dealing with continuous functions, and their inner products are integrals. If we were to look at more exotic spaces other than Rn and allowed the vectors to be other than vectors in Rn, we could certainly take the vectors to be functions, and we could still have inner products. And those inner products wouldn't be given by the sums, like dot products are for us in Rn, but would be given by integrals. Not often the realm of theory of matrices, and the intent of this class is really Rn. More that idea would lie in the realm of a functional analysis. A lot of those computations, in fact, are done in things called Hilbert spaces. But Schmidt publishes in 1907 a paper where he uses this process, and he mentions Gram's work, and it's from that paper that the title Gram-Schmidt process gets put on this technique. These comments are from the MacTutor History of Math archive website. Excellent place for a whole bunch of history of math, some of it pretty mathy, technical. So it's a good reference to see who was doing what and when, to get some clue as to how some of these ideas fit in a bigger picture. And Fraley and Beauregard's linear algebra has a number of historical comments in it as well. So I borrowed from those two sources on this. Shifting gears a little bit here. Hey, this Gram-Schmidt process holds in Hilbert spaces, as I mentioned. I've got some notes posted out there where we're going through and creating a orthonormal basis for an infinite dimensional Hilbert space. So common techniques in functional analysis as well. Take a look at that. This will give you ideas of how to deal with inner products in terms of integrals as well. Okay, but one parting comment about orthonormal bases. If U1 through U sub n is an orthonormal basis for a vector space, then we can take a vector x, write it as a linear combination using, say, coefficients c sub 1 through c sub n. Then Parseval's identity says, since you've used an orthonormal basis, it's easy to find the norm squared of that vector. You just take the sum of the squares of those coefficients, of those c sub i's. Piece of cake to prove. Norm squared, that'd be the inner product of x with itself. I think we did something like this upstairs in our computations. You take the inner product of x with itself. Well, geez, these things are orthonormal. A bunch of those inner products are going to be 0. And a handful of them, in fact, exactly n of them, are going to be 1. And that's where this condition on the coefficients will come from in terms of norms. Okay, now, still a little bit of a hodgepodge of topics left in this section. Here we're going to talk about systems of equations, which you should know intimately from sophomore linear algebra. Here we're using slightly different notation. Following Gentle's introduction of the notation, I'll shift gears a little bit and modify the notation so we can see it in a more familiar way of how you dealt with it probably in sophomore linear algebra. Okay, so we're going to start out with a collection of linearly independent vectors from Rn, say c sub 1 through c sub m. So we're starting with column vectors, m column vectors, each with n components. That's what they're getting at here. And a vector from Rn, call it x. Also a column vector, think of it as having entries x1, x2 through x sub n. Unknowns, that's where we're going because we're trying to deal with systems of equations here. And some constants, b1 through b sub m. We're ultimately going to make a vector out of these as well. But what we're getting then is the following system of m equations in n unknowns. We'll take C1 transpose times x, all right. So what they're up to with this is, remember we were treating these as column vectors. So to get the matrix product to work, or if you like, it's a dot product. To get the matrix product to work, what we'd have to do is transpose this first vector to make it a row vector. And then we'll have this row vector with n entries times this column vector, which also has n entries. It'll give you the linear combination, first entry in this vector times x sub 1 plus second entry times x sub 2 up through last entry times x sub n equals b sub 1. So it gives you a single equation. The right-hand side is just a constant b sub 1. The left-hand side is, if you like, I want to say it's c sub 1, x sub 1 plus c sub 2, x sub 2 up through c sub n, x sub n. But those are components of this first vector, c sub 1. We've used c1 through c sub whatever to indicate vectors, so that's not the best way to illustrate it, but it's a linear combination of the x's set equal to b sub 1. Those coefficients are coming from this vector c sub 1, and similarly taking different coefficients. All right, so we've got m different linear combinations of x1 through x sub n set equal to b1, b2 through b sub m, respectively. N unknowns, the components of x, it's a vector from Rn, an n vector, as Gentle likes to say, and m equations, one for each of those m vectors, c sub 1 through c sub n. Transpose gets thrown in, so the matrix product makes sense. Passing observation, well, if I'm treating these things as 1 by n matrices, and I'm treating this as an n by 1 matrix, then this right-hand side technically would be treated as a 1 by 1 matrix, you know, the dimensions from when you multiply matrices together. Give me a little break on some of that notation, but arguably this right-hand side, I'll put square brackets around them because they're 1 by 1 matrices. Maybe it is a little more familiar to you when we went through and we treated this as a matrix C times a vector X equals a vector B, where C has as its ith row the row vector C sub I transposed to make it a row vector. That's probably a more common notation from your previous experience, but it's the same thing. All right, we had started this with a conversation that these C1 through C sub m's are given to be linearly independent. Okay, let's go down here and see what that implies about the system of equations. We've got m linear equations and n unknowns. Since the rows of C are linearly independent, highlighted up here, that was how we started the conversation, with linearly independent vectors, those C1 through C sub m. So the rows of C are linearly independent because the rows of C are those vectors, C sub 1 through C sub m, okay, transposed. Then each column of the row echelon form of C contains a pivot. They were linearly independent. Every column will have a pivot. I take that back. Every column I don't want to say this. If m equals n, every column will have a pivot and we'll have a unique solution. If m is less than n, we'll have the maximum number of pivots. We won't necessarily, this isn't quite right, we won't necessarily have each column containing a pivot. We'll have each row containing a pivot, and each column will contain a pivot as well if there's enough room for them. So this is a bit of a misstatement here. We get a unique solution when m and n are the same. If n is bigger than m, if there's more unknowns than there are equations, then having those columns be linearly independent will give us solutions, and we'll have free variables. That's what will come out of that. So we'll end up with n minus m free variables. The linear independence guarantees a consistent system if you're concerned with that. But what we'll either get is a unique solution if there's enough equations to determine a unique solution, same number of equations as unknowns. This is the two conversations we're having. If there are not that many, and we are taking m less than or equal to n because of the linear independence, then we'll have free variables, and I can tell you how many free variables. So this is just an alternate notation for a bunch of stuff you do near the beginning of sophomore linear algebra in terms of systems of equations. To put some geometry on systems of equations, as you did in linear algebra, if we have m equations and n unknowns, as given above, the set of all vectors x that form solutions are called a flat or an affine space in Rn. I think affine space is a fairly common word, though when I've taught linear algebra, we use the word flat or k-flat. It was the dimension of what we're dealing with in these little spaces. We'll elaborate on this in a little while as to what a k-flat or an affine space is. They need not be themselves vector spaces. What they are is translations of vector spaces in Rn. More of that shortly. If all the right-hand sides of the equations are zeros, then the systems of equations is homogeneous. And when dealing with homogeneous systems of equations, we're going to see that we actually get a subspace. That's the next claim. If m equals 1, you only have one equation, then the solution's called a hyperplane. If m equals 1, we had n unknowns and one equation. How many free variables are you going to have? Well, all but one of them will be a free variable. So you'll have n minus 1 free variables. What you'll end up with then is a translate of an n minus 1 dimensional space as a subspace of Rn. So we'll have an n minus 1 dimensional subspace of Rn translated. Such a thing is called a hyperplane. So need not itself be a subspace, but the reason these are called hyperplanes is because think about R3. If I draw a plane, regular old two-dimensional plane in R3, cuts R3 in half. Yeah, an n-1 dimensional subspace of Rn, it cuts Rn in half. There's a kind of an above and a below a hyperplane, or hyper above and hyper below. So that's the reason the word plane is used, even though the dimension is not 2. I mean, we're used to thinking of two-dimensional things as planes. Here we got an n-1 dimensional thing. Well, I guess it ain't a plane, it's a hyperplane. And again, we'll talk about translates here in a second. When we look at homogeneous systems, claim is, you'd show this in sophomore linear algebra, the solutions to a homogeneous system of equations form a subspace. These others need not form subspaces, as you saw in linear algebra. Let's take a look at a proof of that, because it's easy, it's computational. We'll do it in terms of this notation that's introduced in our textbook. All right. We need to only show that we got a subspace, that solutions to a homogeneous system is closed under linear combinations. What was a subspace of Rn? Was a collection of vectors closed under linear combinations, or closed under scalar multiplication and vector addition, closed under the things that you do to vectors. All right, so let's take a couple of solutions, x1 and x2, and a couple of scalars, a and b. Assuming x1 and x2 are our solutions to the homogeneous system of equations, then we can plug x1 in for x and get zeros out on the right-hand side. We can plug x2 in for x and get zeros on the right-hand side. Maybe just a passing comment. Remember, these are vectors, right? The x1 vector and the x2 vector is replacing the x vector. These right-hand sides, these are actually scalars, the way we've got the thing set up because of the notation we're using. And these, of course, these are vectors as well. Okay, so here's the two systems of equations written out with x1 plugged in for x and x2 plugged in for x. We said they're solutions to the homogeneous system, so we'll get the zeros out. All right. So if we take a linear combination, ax1 plus bx2, multiply on the left by c1 transpose, it's effectively a matrix product. Properties of matrices allow us to distribute and get scalars out front. There's your c1 transpose x1. Hey, c1 transpose x1 equals a scalar 0, so we'll get a 0 there. There's a c1 transpose x2, same story, get a 0 there. So we've got scalar a times scalar 0 plus scalar b times scalar 0 equals scalar 0, just to emphasize when we've got vectors and when we've got scalars. And that happens throughout. So you do the distribution. We can also write it in terms of matrices and be a little bit easier than all this subscripted C stuff. But indeed, we get that the linear combination is also a solution to the homogeneous system of equations. That's enough to show closure under linear combinations, by induction if you like. And so we've got a subspace of Rn. So back to the notes. Solutions to homogeneous systems form subspaces, not true for non-homogeneous systems. Non-homogeneous systems of equations can't have a solution set that contains a 0 vector. If I plug in zeros for the 0 vector for the x vector, we're going to have to get scalars of 0 out. So if we have a non-homogeneous system, the solution set can't contain the 0 vector. Well, if it can't contain the 0 vector, then it's not a subspace. Every subspace of Rn has to contain the 0 vector. Every vector space has to have a 0 vector. So if we look at solutions for non-homogeneous systems of equations, then they can't be subspaces. This is where the translate stuff comes in. So a flat, or if you like an affine space or hyperplane, may not be a subspace. So we'll describe it in terms of translates of subspaces. So what we'll do is get all vectors of the form. We'll take a span of v1 through v sub k and translate those. Add a single translation vector to all of those. And you probably did this kind of thing in sophomore linear algebra. You may have defined a plane as a 2 flat, the dimension's 2 for plane. So it'd be a translate of a 2-dimensional space. Lines are translates of 1-dimensional spaces. So when I draw these things with all my standard position disclaimers, then we get things that look like planes and things that look like lines when we have 1- and 2-dimensional affine spaces. But they need not pass through the origin. That is, they need not contain a 0 vector. All right, probably something you haven't seen before. They introduced cones, which is something you have seen before. So it's a very suggestive term. Try to relate it somewhat to ideas of cones from your previous experience and the stuff we saw earlier in here about cones. We're going to take a set of vectors V, vectors from Rn, not necessarily a vector space, not necessarily a cone. Earlier, a cone was a cone was closed under non-negative scalar multiples. A convex cone was closed under linear combinations, where the scalars you used in those linear combinations were non-negative. Here we're defining a dual cone. This involves really some inner products, involves angles. The dual cone of this set of vectors V is denoted with an asterisk, V star. Wherever you have this idea of duality, it's common to use an asterisk to indicate it. Do it in normed linear spaces and probably graduate real analysis too. You do in graph theory. You find duals of graphs when considering planar graphs. But we get the dual of V star to be all vectors Y star and Rm such that Y star transpose times Y is greater than or equal to 0 for all vectors Y in this set V. All right. Y star transpose times Y. That's just really an elaborate way of saying the dot product of Y star and Y. And we're treating, at this stage, we're treating all these vectors as column vectors. So we got to do the transpose thing to get the product to be meaningful, like we did with the C sub i's that we had upstairs. But really, it's just the dot product, or in this class, an inner product. Well, if it's really just an inner product, then that's related to angles. So we're saying the inner product is greater than or equal to 0. That has implications about the angles between Y stars, elements of V star, and Y's, elements of V. The polar cone of V, denoted with super 0, V super 0, is, I mean, it's kind of the same thing. It's all Y sub 0 and Rn such that Y sub 0 transpose Y is less than or equal to 0 for all vectors Y in this set of vectors V. Okay, so we've got really inner products are non-negative and inner products are non-positive in a dual cone versus a polar cone, respectively. Okay, obvious claim. Hey, if I take a vector Y star up here in the dual cone, then the negative of that vector, negative Y star, here it is, must be in the other cone, in the polar cone. So if I throw a negative sign on a Y star that satisfies this, of course, we can get that scalar negative out, move it to the other side, multiply both sides by -1, reversing the inequality. And we find that negative Y star must be in V sub 0. Similarly, if we take any Y sub 0 and V sub 0, negative Y sub 0 must be in V star. Punchline being, hey, these two sets, I want to say, are negatives of each other, by which I mean you take any vector in set V star, multiply it by negative, you'll get a vector in V sub 0, and conversely. So that's what I mean when I say two sets of vectors are negatives of each other. Any vector in one multiplied by negative gives you a vector in the other. Now, we think of these transpose times vector things as inner products. Okay, I got my little technicality that if I'm treating this side, the right-hand side of this equation, as matrix products, then technically I'm getting a 1-by-1 matrix out, whereas an inner product is a scalar, also called scalar product. Give me a little break on that from not drawing a distinction between a 1-by-1 matrix and simply the scalar that would be the entry of the 1-by-1 matrix. So V star includes all vectors in Rn that make an angle with elements of set V of less than or equal to pi halves. When do you have inner products positive? When the angle between those vectors is at most pi halves, between 0 and pi halves. What's up with the negative? Does that be what, greater than pi halves? We'll find the polar cone by taking the dual cone and just multiplying by negative. So what we got here is, make it bigger where I can see the details of it. Make it bigger still, if it'll let me. Okay, what we got here is a set V of vectors, drawing these tangent lines to it because I want to talk about angles. All right. We want all vectors that are within 90 degrees of all vectors in this little blue set, capital V. Okay, so we'll look at this minimum angle here. I was talking about angles with a positive x-axis, kind of pre-calculus style. Let's draw this line tangent to the set, which reflects the smallest angle. We can go as far as 90 degrees away from that in the positive direction. That's where this side comes from. So we've got a right angle here. All those vectors are in the dual cone, are in V star. If I'll draw a line on the other side, so the biggest angle that we get with the positive x-axis of vectors in set V. And I draw this blue set. Remember, I'm interpreting this as a bunch of vectors with their tails at the origin and their heads somewhere in this blue set. That's what I mean by that set of vectors. This is how we'll illustrate a set of vectors with the thoughts towards standard position. Okay, so the largest angle we get with the positive x-axis is over here. And in order to have all vectors that are perpendicular to all vectors in the blue set, we can go as far as 90 degrees away in the other direction, in the negative direction. So we're going from here, 90 degrees in this direction, from here, 90 degrees in that direction, and that determines the dual cone of set V. Notice it, goes to infinity, as it were. There's no constraints on magnitudes. It's really just a story about angles. So we get all angles, or all vectors in this, looks like a sector in the plane. Of course, I drew a picture in 2 dimensions. And every vector in this region here will definitely have an angle of pi halves or less with vectors in set V. Okay, if I wanted to go to the polar cone, V super 0, I can talk about it in terms of angles. The easiest way to deal with it, though, is just to take the negative of all these vectors. So I'll just take this pink region, flip it about, do some symmetry about the origin, and we'll produce what we get over here. So we've taken anything and looked at its negative, and that produces the yellow set over here. So here's a dual cone, and here's a polar cone. And the easiest way to see it is the way we've drawn it here in 2 dimensions. If we looked at higher dimensions, I can have self-dual sets. If V is a subset of Rn, and it's all vectors greater than or equal to 0, that means all its components are greater than or equal to 0. In 2 dimensions, it'd be the first quadrant. In 3 dimensions, it would be the first octant. In higher dimensions, they're called orthants. So it'd be the first orthant or the non-negative orthant. It'd be all vectors with non-negative components. So what we'd get for V star would actually be that set V itself. Because we've got, in some sense, an opening of 90 degrees, pi halves radians in those orthants. Since we got vectors that far apart, then that's going to constrain you to get that the dual cone of that set is that cone itself. Think in terms of the plane, and it's a little bit easier to see. If we were to go upstairs on this thing, and if we were to stretch out this blue set, that'd involve, make it fatter. That'd involve taking this minimum angle and making it less, which would involve taking this side over here and making this rotated inward. If I were to take the blue set and stretch it all the way over to the positive y-axis, that would correspond to taking this side, this line, and rotating it up to the positive y-axis and forcing us to, remember we kept the right angle here, to take this side and rotate it up to the positive x-axis. So actually, if this included anything along the x-axis and the y-axis, then this dual space would have to include all, only all of the first quadrant in 2 dimensions. Okay, so if we take this non-negative orthant as set V, then it's its own dual, sometimes called self-dual. If we looked at the polar cone associated with that set, we just get where everything was negative, the non-positive orthant. That argument we made above about negatives, that applied whether we were in 2 dimensions or however many dimensions. So there's some examples of cones and polar cones. I've got an exercise. It's a modification of what's stated in the textbook. Shows it for any set, V star and V0 are themselves cones. Remember, what was a cone again? I can take any vector in those and multiply that vector by a non-negative scalar, and we get another vector in that cone. The union is closed under scalar multiplication, but not vector spaces. So these cones need not be vector spaces, and they probably ain't closed under linear combinations. May be closed when I use non-negative scalars, but not when I'm allowed to take arbitrary linear combinations. So we're not getting vector spaces out of these cones. I have limited experience with this cone stuff, but I have seen some research level stuff done and it was in functional analysis where these are used to put orderings on certain spaces. So apparently it has some applications. Nothing I'm terribly familiar with, I'll admit. And one last little topic of cross product. So you'll like this because this is familiar stuff. You did this probably in calculus 3 and in linear algebra. Let's take 2 vectors, x and y, with components x1 through x3 and y1 through y3 respectively, must be vectors in R3. Define the vector cross product of x and y as given here. You're familiar with this. Possibly you saw some motivation for it. In calculus 3, it had a neat property that allowed you to find equations for planes. Maybe you saw motivation for it in linear algebra related to areas and volumes of boxes determined by certain vectors. But let's just take that as our definition and the other stuff as background and state some properties of this cross product computed in the usual way. If we have 3 vectors, x, y, and z, must be from R3 and a real scalar. Then we take a cross product of x with itself. We get the 0 vector out, right? That must be a vector because cross products were vectors, right? Whoops. Cross products are vectors. See the square brackets there? So, right, we're dealing with vector quantities with this. So this is, I think this is the only time I think this is the only time we'll take two vectors and multiply them together in some sense and get another vector. It's this cross product stuff. Not that there aren't other procedures that do that and generalizations of an idea of cross product, but I think this is all we'll see in terms of multiplying vectors together and getting other vectors. Same stuff you saw in linear algebra. They call this self-nilpotency in the textbook. The cross product x cross y is the negative of the cross product y cross x, called anti-commutativity. I don't know about self-nilpotency, but anti-commutativity is a common term to use for the second property, and we'll go through and establish that. Probably a big deal should be made out of this property when you first see it in linear algebra. That as the first time probably you've seen a binary operation that's not commutative, addition and multiplication or commutative. When you see this cross product thing, it's one of the earliest things you may see that's not commutative. Of course, matrix multiplication is not commutative either. You can put your finger on how this is not commutative with a negative sign, and there's some geometric reasons for that you probably explore in those other classes. If we have a scalar ax cross y, we can bring that scalar out or put that scalar on the y, so the scalars move around. That's given here. We get distribution of cross product over vector addition. If we take an inner product of x with x cross y or an inner product of y with x cross y, we get out 0. That's a very useful property. It says in 3 dimensions, the vector x cross y is perpendicular both to the vector x and to the vector y. This is commonly used in finding equations for planes in Calculus 3. And we get, well, we don't have associativity, as we'll show here in a second with an example. We get this little behavior, cross product of x with the cross product of y and z equals this thing on the right-hand side. It's some linear combination of y and z. We poke at it enough, we could probably put some sort of geometric interpretation on that as well. But we don't get associativity, so that's weird. This, I suspect, I will make a big deal out of it. Well, it's probably the only binary operation you can name right offhand that isn't associative. If we take this vector cross product with the cross product of these two vectors, we get out one thing, skipping the computations, but trust me, we'll get 0, 0, -1 out. And if I change the grouping and we multiply the first two together and then multiply by the third, we don't get the same thing. So it's easy to find examples that violate associativity. So that's a rare thing. Even matrix multiplication, it's associative. Dealing with non-associativity is a fairly exotic thing. If you wanted to make an algebraic structure based on this, and arguably something called the quaternions is in some sense related to the cross product. In some sense is a big caveat though. We don't get commutativity there. We do have associativity in the quaternions. There's a bigger structure out there, more exotic too, called the octonions. Maybe that's a place to go to mimic this, where we don't have associativity. Maybe you've heard of the quaternions. Maybe, long stretch, you've heard of the octonions. The quaternions have some useful geometric properties. The octonions, I'm sure they got some sort of weird applications, but they're fairly exotic structure. Losing associativity is a bad thing. So making an algebraic structure out of these things is something we're not prone to do. As I mentioned, hey, you usually use these cross products to find equations for planes in R3. You give me two vectors in a plane in R3, I can take the cross product and it'll give me a normal vector to that plane, and I can use that normal vector to find a formula for the plane in R3. So common Calculus 1 manipulation involving cross products. And there's a link to some of that. And that completes section 2.2. And we'll move on. Section 2.3 is a little bit shorter. The bulk of this course is probably in the material in chapter 3. And some of those early sections in chapter 3 are pretty long ones too. I will see you in section 2.3 soon.